That's short, tight.
All right.
Yeah.
I think I'm about ready to get started. Wow, we skipped a day. It feels like a long time ago, but not really. So there is homework due on Saturday. If you have, so you're not late, but if you happen to have it now and want to hand it in, okay, so as some people already have, that's fine. I'd be happy to take it off your hands, and then you don't have to worry about electronically getting the paper homework to you, okay? If you are still working on it, which is totally fine, or you go, oh damn, I left it at home, then just email it to me in a reasonable way. A PDF is fine, a JPEG is fine, most photo-like formats should be okay. If you, just so we know how this is going to work, okay, if you decide you want to email it to me, I will email you back within 24 hours, okay, so sometime on Sunday, and you'll have one of two things, okay? It will either be a grade, or it will be an I can't read this, okay? If it's an I can't read this, then we'll try and figure out why, okay? Try to make sure it's not blurry, okay, or something like that. You should be able to look at it, and you should be able to fix those, okay? Anybody have a problem getting to something other than JPEG or PDF? Can you do those? Okay. Anyway, you'll either get back a grade or you'll get back a I can't read this. If you get back an I can't read this, then we need to try again. Okay? And we need to come up with I would on Sunday send you something. I would expect that by Monday you would have a second attempt. Okay? So don't throw out your stuff after you shoot your JPEG picture just in case I go, yeah, this did not work. Okay? Good. Probably will. Good? Questions about that? Yeah.
Can you help us out with one of the homework?
Can I help you out with some of the homework?
Yeah, we had a question on one of them, and I was wondering if you could kind of walk us through it.
So here's, I have no problem with doing that, okay? What I do have a problem with is doing that as a main focus of class, okay? And so what I would like to do is move on with the stuff I was going to do now, and then we're going to do another in-class problem, and you might finish early, okay? Or even if you don't finish early, I don't mind staying, a few minutes afterwards to talk about something. Okay? Cool. We'll see. Today, I'm going to be talking about waves and that sort of stuff. We'll be doing a problem. We might have a half hour at the end that we could talk about homework and that sort of thing. Okay? Good. Any other homework-related questions? I did post assignment 2 and assignment 3, so you should be able to see those now. Did people see them? Yes, good. Okay, making sure that it really did work. Good. Okay. And I think those are due Tuesday evening and Monday evening. And then we have an exam a week from this Tuesday. Good. Okay. We also. I realized I was going to bring in the appendix for the 114 lab manual to talk about how to handle uncertainty and that sort of thing. And I realized as I was writing in this afternoon that I had not done that. So I made myself a better note. Okay, I actually did all the things that I made notes of, but I forgot to make a note of that before. And I will post that on Canvas. Okay? But I'll talk to you a bit about the types of this is the analysis in the formal lab and what I'll be expecting, and then you can know that sometime tomorrow, hopefully early afternoon, I'll have that posted on Canvas so you can refer to it. There are in the back part of the lab manual, it talks about 5 things that your lab should address. Okay? One of them is that you should experimentally determine K for your spring. It turns out there's a way that's pretty good to do that, okay? And a way that's pretty good to look at a lot of the data like this. You collected some data that was delta X versus the mass that was hanging on the spring, right? Okay? And you changed the mass to a bunch of different values, and then you measured what this delta X was. This has plus or minus so many millimeters, okay, or centimeters or meters or something. You've got some uncertainty there. This is plus or minus so many grams. That might have been, should have been pretty easy to estimate. You had a meter stick or something like that that you were using to make the measurement. It probably went down to millimeters. And then, depending on what it was you were looking at, it may have been easy to measure to within a millimeter or harder, okay? But definitely attempt to quantify that. This one, you had different masses. They were labeled probably to within a gram. They might have been accurate to within a gram. You might have measured them on the scale over there, which can get down to 1/10 of a gram. 100th of a gram? Maybe 110th of a gram? I think it's 10th anyway. And that would have been better, okay, just because some of these things aren't exact. Also, if you put a bunch of tape on or something like that, that could be a gram or 2. So anyway, this should go into your estimate of what the uncertainty in that is. Then, what you can do is make a graph, okay? And that graph, perhaps you say, here's my mass, and here is delta X, and that graph should, if you add more mass, delta X gets bigger, and this should be a line, okay? You can plot your graph with error bars, okay, indicating the uncertainty in, say, the delta X. Now, I may have drawn those a little bigger, but a full page. Okay. Then, and there is a method in the appendix of the lab manual that talks about how to compute the slope. And the uncertainty in the slope. Okay. Why would we care about the slope?
That's
It's not K here, but it's very related to K. Okay? Basically, the slope of that would give you the spring constant. If this were force, okay, if this were in newtons and this were in, let's see, if we did it like this, if it was in newtons per meter delta X, if you plot it like that, then this slope is K, okay? If you plot mass here, then the slope is not K, but it's related to K because the mass determined how many newtons there was, okay? So, so you might, the right thing to do is convert that into newtons, and then the slope would be K. Okay? If not, then you can use delta X is equal to, it would be, or I'm sorry, you could use the weight that you placed on the spring is equal to K delta X, okay, that weight would be mg is equal to K delta X And then you could see that if you plotted M here, the slope would be K over G delta X. This is still a constant that you could measure. And then if you took that measured slope, if this were M, and you had K over G was your slope, if you took the slope of that and divided by G, you'd get K. Okay? Now there was a question back here? Maybe? Still there? Yeah.
Does it matter which way we use to figure out K?
I don't care as long as what you're going to want to do is use the slope to figure out K, and I want you to use it correctly.
Okay.
So if you do Newton's here and say, this is my slope, that's fine. If you do mass here and say my slope is K, that's wrong, right? Because it's really related to something else. If you switch these around and then handle it correctly, I'm good. So if you've already done the graph and you're saying, I don't want to redo my graph, but I can totally get K from it, that's fine too. Does that make sense? So the important parts, use the graph, use the slope to get K, estimate the uncertainty, estimate the slope and the uncertainty in the slope, and do it in one of the many correct ways. Good? Okay. There are also many not correct ways too, so don't avoid those. Good? Okay, so this should give you, at the end of this, you should have the spring constant for your spring and the uncertainty in it. Okay? The next thing that you were measuring was, you were relating, was period is equal to the square root of K over M. I'm trying to do too much math in my head. Period is 1 over the frequency, which is equal to 1 over 2 pi omega, which is equal to 1 over 2 pi square root M over K. Right. So one of the things we were doing was changing the mass and looking at what was going on with the period. Yes? Okay. And this formula predicts a relationship, right? It predicts that if you do K, which you now do, and you know 2 pi, if you plugged in a mass, you could find the period. You collected T versus M data. Okay? So, just like over here, you could make a plot. Okay? Now, you wouldn't expect M and T to be related linearly because of that square root. Okay? But if you square both sides, you end up with T squared is equal to 1 over 2 pi squared M over K. Okay? So, if you were to make this sort of graph, if you were to say, here's my mass, here's period squared, okay, you would expect to get some sort of line, okay? You'd have data points that are distributed around it, and then you can estimate the slope and the uncertainty in the slope. What would you expect the slope of this to be? What's the formula for a line? If you were doing algebra. Wait. Y equals mx plus b. Yeah. Okay. So we often learn that for an equation for a line. Okay. And the picture would look something like this. We'd say y is on this axis, x is on this axis. Here, this is the slope is m, and b is the intercept. Okay. Now, so you want to sort of generalize this. You want to say, well, y is the thing on my vertical axis. X is the thing on my horizontal axis. It varies. M is a constant, okay? And B is some constant that I'm adding to it, okay? If our formula is this, t squared is equal to m over 2 pi squared k, okay? And we plot this graph, what's on the vertical axis?
Just t is 2 pi squared instead of 1 over 2 pi?
T is 2 pi squared? That what? This is right, isn't it? And isn't that right? No. You're right. Sorry. My 2 pi should be up here. Because omega is 2 pi f. This is what I.
Okay, yeah.
Yes, you're right. Good? Better? Okay. Now, if we plot this, if we plot t squared versus m, t squared is on our vertical axis. Okay? So this t squared is also, we've written it out in the form where the thing on the vertical axis is what is equal to the other thing, right? The other thing has our variable, okay? This is m instead of x, so m is the thing on the horizontal axis, and then it has some constants, okay? So this here is the slope. Yeah? Okay, because that's the constant that you're multiplying by. This constant times m gives you t squared. That fits the form like mx plus b is equal to y. Yeah? Good? Okay. So if you make this graph and you measure the slope, okay, it should match this. So you can measure that slope and you can get a number. Okay? And you'll say, this is 5 plus or minus 2. And then you can say, well, what I would have predicted is 2 pi over k. This is what I had for k. Does 2 pi over k match what you got for the slope? Okay? And it has some uncertainty. If they overlap, if you've got like 5 plus or minus 2 and 4.5 plus or minus 1, you go, oh yeah, those agree pretty well, right? Because 5 plus or minus 2 incorporates 4.5, they overlap. If you get, this slope is 10 plus or minus 1, and when you calculate 2 pi squared over k, you get 3 plus or minus 2, then you say these disagree, right? Because 3 plus or minus 2 doesn't match, doesn't overlap with 10 plus or minus 1. Yeah? Right? So that's how you can compare the quality of your results. Okay? In your conclusion, we say, this is what we measured, and that's what we got. The other thing you're going to be doing is make a prediction of what the motion looks like. Right? So you can, we said it, you just split in the third part, you displace the spring by 15 centimeters, it oscillates back and forth, and you know the spring constant K, you know the mass that you put on the spring, you know the formula, you know that X is equal to A cosine omega t, okay, which is equal to A cosine square root of k over m times t, okay, should give you this graph, and you can figure out what that is because you've measured k, and you've got an experimental measurement of k and m, and this amplitude is 15 centimeters, and you can use your calculator and predict what this should look like as a function of t. And then you can compare it to the one that you measured. Yeah? You can do that not only with the position, but also with the velocity and the acceleration. Seem okay? Okay, so I will post by tomorrow afternoon the instructions for how to do this slope and uncertainty of the slope, okay? But this should give you an idea of what to do with the data in your lab. Yeah? I think I also posted on Canvas that the formal lab is due next Saturday, which is what we discussed in class. And feel free to hand in a draft sometime next week.
Week from Saturday, right?
A week from Saturday?
Yep.
It's a week?
Well, you said next Saturday,
Yeah, next Saturday.
so week
Yeah.
from Saturday.
Yeah, July 9th,
Okay.
not 2 days from now, okay?
Okay, yes.
But yeah, that's right, okay. Second, it's not this Saturday, it's next one, okay, but the one at, that one, the 9th, yeah, okay.
Yeah.
Good,
I'm not confident.
so,
I already did this problem.
it's time for us to discuss some new phenomena. Our new phenomenon is related to oscillating motion, but it's not the same thing, okay? It's, what we're going to talk about
Dude, I'm not gonna.
is waves,
I totally could.
okay? And so, we've got a number of different examples,
I'm just gonna.
but the first thing I want to talk about is the
What? If you need more
Is-
time, just do a balloon.
just sort of like what we did with simple harmonic motion. We talked about, what is oscillating motion, and then we talked about things like amplitude and period, frequency, and we started to label these things that describe the motion. With wave motion, we have some similar stuff that we need to talk about. Okay. One of the examples of wave motion is a stretched spring, okay, or a spring will do this. And if you stretch something like this, and you do something like clef it, okay, I disturb it a little bit over here and let it go, okay, you can see a pulse move down the spring, okay. If you notice, it took off this way, okay. It hit the other end and then it bounced, okay. But if you imagine a very, very long string, it wouldn't have bounced. It would have kept on going, right? It was just moving along, okay. So we can, well, there's some things to notice about the spring, okay. First of all, what's moving? What's moving? The spring. How is the spring moving? Up and down. Yeah.
It's like
So-
a wave.
How's the wave moving? Which way does the spring go? The spring goes up and down. Which way does the wave go?
The same.
Does it go up and down too?
It just kind of carries throughout the amount of force that you put in.
What?
It just kind of carries that same shape like all the way to their side, and then it'll.
Yeah. So there's this shape that moves along the spring, right? So I'm plucking it like this. So I've got this end is up and that end is down, and I'm going to let go. So, but you saw that shape propagate across the spring, right?
Yeah.
Did the spring propagate across the spring? Did this coil go that way?
Yeah.
Huh? It did?
No.
I mean, maybe a little bit. It might have wiggled a little bit this way, but it's not like this coil is going all the way down like that, right? It's not like the spring is going that way. What's happening is the pulse is going that way, right? And this is a different kind of motion than we've talked about before. Typically, when we said something, if I go, how is this tape moving? And I go, do that, the tape goes with it, right? Okay? But here, I shake the spring and the pulse goes that way, but the spring does not. Yeah? Okay? So that's a typical thing about waves, is that the actual material wiggles, okay, but it in itself doesn't move, okay? What sort of things make this pattern, wave-type patterns? We got this spring. What else does that? Water? Okay. So I have a little water tank over here. You want to come look?
Do I ever?
Don't you? Of course you do. Of course you do.
Here,
Yeah.
underneath.
So it's rippling right now just because it's shaking, but I can do something like take my finger and stick it in here, and when I do, do you see a pulse leave my finger? Okay. Now the water itself doesn't go with it, right? There's a disturbance in the water, right? And that moves as a wave, okay? But it doesn't. But the water itself isn't going. There's also something different about this than that. What is the shape of those waves? Circular, okay, and they do what? How do they travel?
Radially outwards.
Yeah, radially outwards. They get bigger and bigger and bigger. It's not a circle that's moving across this way, but an expanding circle from where I pop my finger in. Okay? It still hits the edges and bounces off, just like it does with the edges over there. Okay? So we'd say this is a two-dimensional wave. Okay? It exists on the surface of the water, okay, and it spreads out. Okay? This is a one-dimensional wave. Okay? It moves along the spring and it just stays on the spring. Are there three-dimensional waves?
Sound.
Sound. Yeah. So how does sound work?
Disturbance in the air.
We disturb the air. And?
Send wave frequency through the air.
Okay, yeah, okay. So just like we did here, we disturb the air. There is a pulse, okay, that it expands, and the pulse can, if I talk, and there are sound waves being created by my mouth and larynx and all, I don't know, I'm not a biology person, but somewhere in there, okay, then they leave and they spread out in all directions, okay? All of you can hear this two-dimensionally around the room, okay? But if you lay down on the floor or, get up in the ceiling, you can hear it as well, right? So it spreads all the way around that way, not just in a plane or in a direction. Okay. Cool. So waves can be one-dimensional, two-dimensional, or three-dimensional. They involve a disturbance, okay? When you disturb, I can disturb this piece of tape, right? I disturbed it, and it doesn't, and it actually moved, right? I disturbed the water, and the ripple moves, but the water doesn't move. The water comes back. When I disturb that spring, the spring moves, wiggles, but it doesn't, the spring material doesn't move down the wave. It comes back. Why does it come back? The air does that too. If I start talking, it's not like you feel a wind coming, a wind coming off, and blowing away. You just hear the sound waves, but the air is wiggled but relatively still, right? Why does it come back? Why doesn't it stay where it was?
It's a surface it can't break through. It's a surface that it can't push through. And it has to.
It hits something it can't. So definitely when it hits a boundary, okay, like that pole over there, okay, the disturbance can't go through that. Why, when I disturb the spring, when I wiggle this, why does the spring, why don't these coils just go down that way? Okay, or why don't they keep going up? Why do they come back?
I think it's Monday.
Yeah?
They keep coming back because the leftover energy use is transferred somewhere else before we bounce it back a little bit. I mean, it just bounced back because you have a wall that just.
No,
Well, if you applied force to the spring, it went through the spring, right, and then it needs something to bounce back off of, because it couldn't absorb it again.
all right, let's get rid of the wall.
Ooh, a bigger one.
Okay, so I got a slinky, okay? And the cool thing about the slinky is that I can throw this out on the ground and there's no wall on the other end, right? Can I send waves on this without the wall? Oh, yeah,
I'd say you could, it wouldn't come back. But I wanted to say,
yeah.
can we consider like the shape of the material that we're working with and the material that we're working with also as having like those type of properties that.
Definitely the material has properties. Are you talking about the shape, like?
Yeah, like if that was just a string and you flicked it, you would see maybe like a small wave shoot one direction then maybe come back slightly, but it's not going to retain that amount of force because of the shape that it's lacking. Like that, because it has a spiral shape, it holds like tension a little bit better, right? So, I mean, maybe not tension isn't the right word, but.
No, tension is the right word, but I think actually it has less tension than spring.
Yeah.
Because, you don't have to stretch this very hard, but the tension on this is pretty weak, right? If I stretch a spring, and, if I pull this, a centimeter apart, I can do this easily with my hands, okay?
Yeah.
But I can't do that with a piece of cotton string, right? Because it's too tight. And
So
I think with a piece of string, the tension would be greater.
Yeah, I guess elasticity is like the word I'm looking for.
Oh, okay. Yeah,
Yeah.
this is actually, well, this is,
Maybe, yeah.
it bends easily and comes back. So with a little bit of tension, you can stretch it,
Yeah.
okay? It's a stretchy material.
Yeah. A malleable.
Okay. Is it deforming? Am I, when I do this, do I break the spring? No, it comes back to where it was before. Oh yeah. So if I take the spring and I lift it up, what do I feel with my thumb here on my left hand? A normal, I feel at least a force by the spring. Which way is the spring pushing? Down. So if I lift the spring up, the spring gets pushed back down. Okay? So if I lift the spring, what if I, instead of lifting the spring, what if I push the spring that way? What if I say I'm going to stretch it like this? Well then my finger over here feels the spring pulling back. So when I disturb the spring from equilibrium, wherever it was sitting, it gets pulled back towards where it was. That's kind of like simple harmonic motion, yeah? Okay? And actually that is why, in all of the cases that we just talked about, when I disturb the medium where the wave is, the medium pushes back. Okay? So if I lift the spring like this, the spring gets pulled back this way. Okay? And so the spring doesn't keep going that way. The spring doesn't go that way. It just goes back to where it was. Okay? If I stretch it this way, it gets pulled back this way, and I send a disturbance down the line, but I don't send the actual spring. Right? When I was messing with the water over here, okay, and I stick my finger in it, I make a little hole in the water, okay, and the water's pushing back on my finger. When I lift up, the water comes back in, okay. So I move it away, it comes back. Sound is a little harder to visualize, okay, but you've worked with maybe an air pump or something, and you compress air, you squish it down, and it pushes back on you, right? Or if you pull the other way and create a partial vacuum, it pushes back the other way, okay? If the air is a certain pressure, and if I squish it or stretch it, okay, then it goes back to where it was, okay? And so the sound wave, the water wave, the string or spring wave, they both would do the same thing, depend upon what the require that they get pushed back to where they were, okay? And it does depend upon the material, okay, as to how fast it would go. I don't have a liquid other than water. I do have another spring. Well, actually, before I take this off, there's something I want to try. Okay?
That's my first start.
We're not really going to measure how fast it is, but let's just watch this a couple times and get an idea of how fast it is. Okay? If I pluck this string and send a pulse across,
So cool.
there's the speed, right? Okay? It goes about that fast. What if I make the spring tighter? What if I change the tension? Faster or slower?
I'm gonna move faster. It's gonna move faster.
So I'm going to change this by doing this.
Organic rock stars.
Huh? Okay, it's tighter. Faster or slower?
Faster.
Faster? Faster? Yeah. Okay, so it turns out that the tighter I pull the string, okay, or spring, the faster it will go. The bigger that restoring force is, the faster it will come back to its position, and when it changes things nearby, it goes faster.
Okay, what if you had a really, really long string?
I can,
Really long string that goes taut.
but you can imagine sending waves down this meter stick, right? You could imagine,
But it'll have to stop at some point.
no, shaking it and seeing the pulse go down that way. It,
That's the end. I
I
think.
mean, go, all right, this meter stick is 2 meters long, so it's, and that, is probably more like 8 meters. So this is about a quarter of that distance, okay? If I plug this in and the wave propagates down there, it goes very fast. It's a different material, okay? Different tension, okay? The tension in this is incredibly huge. Well, actually, when I plug it like this, the tension isn't that big because this is kind of floppy, okay? But if I were to do this and plug it this way so that my disturbance this doesn't bend very much
It's the brain.
this way, okay? And so it's going to travel really, really fast, okay? I can send waves down these rods by dropping. If I drop them, I make a disturbance on the other end, okay? And what are you hearing?
Sound.
Impact.
You hear actually, does it sound sort of like a ring? Yeah? What you're hearing is I disturb this end of this rod. The there's a vibration that goes through the aluminum up to the top here, turns around and goes back, and the whole thing starts ringing like a bell. Okay? It does at, well, the speed at which it goes through this, okay, is very high. It'd be like the speed of sound through aluminum. Okay?
Like a guitar string or whatever.
Well, a guitar string is plucked
It would be more like
differently,
that, but
okay? But yeah, so
Same concept.
we should talk a bit about that.
Strings,
Right.
percussions are cool. Strings, you know?
Sometimes your wave is because your wave is traveling in a particular direction. Okay, on this spring, the waves travel this way. If I pluck it perpendicular to the way things travel, what we'll do with that, that's called a transverse wave. Okay, so that's transverse. It's across, transverse, across the direction that it's traveled. Okay, the other type of wave that we, that's also a transverse wave. Okay, so that there are many ways I can pluck it perpendicular. It doesn't have to be vertical. It could have been horizontal. It just can't be in the direction of travel. If it's in the direction of travel, that's called a longitudinal wave. Okay, and it turns out this spring can do both. Okay, if I bunch it up like this and let go, you can. There's a little bit of a transverse thing going on, but could you see a longitudinal pulse? Okay, that goes down that way. You can see them with slinkies too. Can we run this down the middle of the room? Somebody want to grab the other end?
Ryan. With your organic rock
You
stuff.
got it? Okay. Why don't you, only some of us can see it. Go ahead and set it down on the ground. Okay? So I can send a longitudinal wave on the slinky wave.
It'll be
Okay.
really hot.
Yeah?
And
Do
then
they-
it's really low.
Can you separate them or are they
Yeah.
racked? Hopefully it's not racked. Cool. Yeah. So we can do a transverse. Okay, transverse wave like before, okay? Or I can do that and you can do a longitudinal wave, right? Okay? So those are both kinds of waves. You can see it better on the slinky, it goes slower. Tension's even less. Notice those are slow moving waves compared to these, right? Okay, because again, the tension is less. Yeah?
Yeah.
Cool.
He's flying.
Oh, yeah. Go ahead and your hand is
10.
10?
Yeah.
Here, I will hold this, I will let go. Go ahead and shake it. See, they travel even if there's not a boundary at the other end, right? All they need is more spring on the other end, right? Yeah. Good? Cool.
Hell yeah, team.
Good job.
Yeah, good job.
It was on video.
Yeah. With the fucking superstar.
So make sure you send a release at the end of class.
And I want your autograph.
You also need your social security.
Name, address.
Debit card.
Yeah.
For no reason.
So we can deposit direct deposit.
And direct withdrawal. And your savings, say goodbye to that.
You won't need it.
Yeah. In fact, you still owe us money.
Oh,
It's worse. And more profound. And we're now living at your house. And we're now celebrating Mother's Day with your mother. It just gets worse.
Okay.
And we've already bought you a casket with a graveyard.
So, I want to talk a little bit more about the dynamics of the speed at which the wave travels, okay? Certainly, we did see it move with it was traveling from one end to the other. We saw that the tension changed the speed. If we increased the tension, it increased the speed. The other thing that can affect it, and we were sort of getting at that, is the material that it's made of, and in particular, how massive it is, okay? Things that are very massive are more difficult to move. They're more difficult to shape. Things that are less massive, okay, are easier to shape, okay? So, if this was same tension, okay, but a lighter weight spring, okay, you would expect it to go faster, right? Okay? And if it was a heavier thing, okay, you would expect it to go slower. Yeah? Because the same force isn't going to shake it as easily, right? Okay? So, what we end up with is that the velocity of the wave is equal to the square root of the tension divided by mu, okay, which is the mass density of the spring. Okay, so mu is equal to the total mass over the total length. Okay. Right. So, and you don't, it's written like this, but really, if you had a section of the spring and you said, what is the mass of this, okay, divided by the length, that would be its mass density, the number of kilograms per meter, okay? And it turns out that, even if you said this is an infinitely long spring, okay, it could still have a mass density, right? It would, maybe it's, half a kilogram per meter, but it just goes on forever and ever and ever, okay? Then you could predict what the speed is of those waves, okay? Good. We will do a lab.
Tuesday.
Yes, we will do a lab on Tuesday, which I think is waves on a string, where we'll be adjusting the tension, we'll be measuring this mass density and verifying that. I think we also do a lab on Thursday, speed of sound. Okay.
Ooh, cool.
So,
Right.
yeah. Okay.
Right.
Good. I've talked for an hour. Let's take a break. Okay.
Yeah.
Let's take
Throw a frisbee with me.
Wish I did.
Sometimes what you have is just a pulse, right? Something like that moves as one single thing. Okay? But sometimes what you have is something that's continuously shaking the medium, and then you get a pattern like Tan showed. I was going to do it on here, but because of the boundary on the end, it doesn't work as well. But if we take the slinky, and shake it like this. Yeah, you were doing a great job. You want to do it again? Okay, here, stretch that out. Okay. Well, actually, that's not bad. Okay, notice that I've got one pulse following another pulse, right? And I've just got one after another traveling down the end of the, traveling down the end of the spring, right? So the pulses are moving this way, okay? But they're occurring one after another, okay? In that case, instead of seeing like a single pulse that moves, we've got this continuous thing. And so, thank you.
I know, that's like interesting.
It's like we're hanging a noose on.
So, that pattern was roughly sinusoidal, okay? And meaning that if we say, here is my position X, and here is the amount of disturbance Y, okay, then what we have is something that looks like this, and it repeats, okay? And you go, oh, this is the same graph that I drew the other night, but it isn't, okay? Because the other night, this horizontal axis meant time, okay? And in this case, the horizontal axis is a spatial axis, okay? We saw the wave, okay, distributed along the direction that it was traveling, okay? So, if we wanted to describe this wave, notice that it does have some of the same things that we saw with simple harmonic motion, okay? It has an amplitude, right? There's an amount that it was disturbed. If this were, in the case of that spring, when I was shaking it, it might be a distance of so many centimeters. Okay? In the case of a sound wave, it might be pressure. Maybe this is the atmospheric pressure, and this is so many psi above atmospheric pressure, and so many below atmospheric pressure. Okay? And that's what this would be measuring. In a longitudinal wave, it might be how far the coil was disturbed from its original position. Okay? And it could be disturbed one direction or the other direction. So this doesn't mean it has to be a transverse wave. This is just how much it was disturbed. Okay? And so we could say this has an amplitude. Also, there is a distance, there's the idea of a cycle, the distance from this peak to peak, okay? When we were talking about simple harmonic motion, that was time, right? But now, this is actual distance. This is how many meters there is between one peak or another, okay? So this is called lambda, which is the wavelength. And then we can do something similar to what we did the other day, where we said, all right, if the wavelength is the distance that it takes to do a complete cycle, and we could say that y, the amount of disturbance, is going to vary as we move along the direction of the wave, and after we've gone through a complete cycle, it'll come back to where it was before. So we could say for that wave, it's equal to A cosine, and then the amplitude, the disturbance is varying as we're moving along x, okay? So it's going to move along x, and after it's gone through one wavelength, okay, it needs to have gone through 2 pi. Okay, so if this was one wavelength, I would want to be giving 2 pi to cosine. So I can do this. I can say x over lambda. So this starts off at 0. By the time x is equal to lambda, that would be 1. And then if I multiply this by 2 pi, right, then this would give me that graph, right? Okay. If I get halfway down the wavelength, so I'm at lambda over 2, I'm giving it pi, okay? And then when I get to 2 wavelengths, I get myself a lot of room, so I'm going to shrink it a little bit here. But a little bit later, this peak, the waves were moving that way, away from my hand. A little bit later, this peak is going to be further along, right? So this peak will be over here, okay? And then this trough, instead of being over here, will be over here. And this will go like this. That peak will be moved over. That peak will be moved over down here. Okay? And it'll be the same wave, but shifted, right? It's shifted over this way. Maybe more like that. Okay? And so what we can say is that, well, this should not only be a function of the position where we are along the wave, but it should also be a function of time, right? Because time matters as well. And the effect is this bump over here, okay, used to be where used to be at x equals 0. Now it's at a location that's somewhere in the positive, right? Okay. So what I need, so if this is somewhere in the positive, and well, back then it used to end up being something like this, but I need to make it look like this. In other words, I need to make this spot here look like what 0 used to look like. And this spot looks like, I need to make, I don't know, this peak here is shifted over. I need to make this spot look like what that used to look like. Everything needs to shift this way, okay? So if I want to make this spot look like what 0 is, I need to subtract off something, okay, as time goes on, so that this position x becomes, okay, where this spot was over here. Okay? So I need to shift the graph as time goes on, and I need to subtract something to get it to move like this. So this is going to end up being minus, okay, well, I'll write it the way your book did it, 2 pi t over over the period. Okay, so if this whatever the period of the wave is, how long it takes to repeat. Okay, if we wait that much time, this ends up repeating. Okay, and okay. Anyway, this would describe what that wave looks like as a function of x and then as a function of time. Okay? So, yesterday, when we were looking at simple harmonic motion, okay, one of the things we did was we said, well, we had A is equal to cosine omega t, right? Because omega was 2 pi over tau, right? Because omega is 2 pi times the frequency, and frequency is 1 over the period, okay? So we can say it's omega t. We go, hey, 2 pi over lambda, 2 pi over the wavelength, it'd be nice to have a symbol for that. Your book doesn't use it, other books do. And unfortunately, it's called K, okay? But if you're doing these statistics with other books, and you're saying cosine K x minus omega t, that's this same idea. This is called the wave number. That's the angular frequency. This is the wave length. That's the period. Okay? You can be fine working with this, but be aware that that is out there. Cool. So this is kind of a weird thing. If you know a particular time, this would just become a number, and you would see that you can think about what the behavior would be if we looked at some particular x position, or if we looked at some time and we wanted to see what the shape is. The shape would always be sinusoidal. Looking at different, if we say, I'm going to look at a particular position, maybe 0, right over here, okay, what we would see is that this spot here would go back and forth just like simple harmonic motion, okay? and it would go with a period of t. Okay? But that's true for any point. If I pick some position over here and say, I'm imagining time going on, every time it goes through a capital T amount of time, it would go through one cycle of cosine. So you could imagine, picking a spot over here and watching this, move back and forth, right? Okay. Or you could say, I'm going to think about, 55 seconds along, what's it look like, and it would be this sinusoidal pattern just shifted. Okay. So that's kind of a. We haven't had functions of two variables very often. Okay. So be aware that that's what that is. Okay. Yeah.
So as things go along, the wavelength doesn't change at all, it stays constant, and then you're just kind of calculating over time where it's going to be at in this wave. Like
That's right.
What the
That's right.
amplitude's
The
going to be
whole
at a certain time.
As we saw with the pulse, the whole shape just moves along. Okay. Now what we're saying is, well, what if the whole shape is a long sinusoidal set of disturbances, like what we were doing with the slinky over there? In which case, they all just move along. Good. Yeah. Okay. It might be nice to think about, well, what does that mean? Well, okay, so we saw that with the slinky. I can sort of get some waves going like this, and so you can see that there's motion in time. Actually, this is a pattern that we'll talk about next time. But you see that there's a motion in time, okay, and a motion, in the spring. Actually, you aren't traveling; they're standing. And the waves we had over here were better with the open end because they didn't stand. With the water waves, you can keep shaking your finger up and down and end up with a pattern of waves that have a wavelength, right? That you can look and see the ripples and see the distance between the crests. And the pattern is that the distance stays the same and they just travel outwards, right? And so they all move together along. It's the same with the sound waves. You can't see sound waves like this and that, but it turns out that we can use this. This is a paper speaker, okay? And we can use that to observe, measure, okay, visualize the sound waves. So you're taking 115. So this is a paper cone, okay, and it is attached to a little coil, okay, a little wire coil, and that wire coil, there's a magnet here, okay. We have,
Are they flaming hot?
No.
Are they flaming hot?
No.
Oh
Not a very
my
good
god.
magnet. Oh, yeah, okay.
Right now.
See, I don't know if you can see, but there's a staple I just stuck to
That's true.
it because it's magnetic there,
I
right? Okay, so there's a permanent magnet in here. There's a coil that's vibrating back and forth. If it vibrates back and forth around the coil, what does that do?
Creates a current.
Exactly. It induces an electric current, right? Okay, so it induces an electric current, okay? And this is hooked up to an oscilloscope. What it will do is it will sense that. It'll measure that. And the way an oscilloscope works is it has a little dot that moves vertically depending upon it's actually the voltage that's applied, the voltage signal that's applied here. And as this goes back and forth and induces a current, it does so because it induces an EMF, which is a voltage, which pushes the current, and it's that. But that EMF is what is sensed by the oscilloscope. And so in the, yeah, I'll turn on the oscilloscope and there should be a, oh yeah, so there's this little dot. And notice that as I talk, the little dot goes up and down. So what's happening is that the cone is vibrating, and and so vertically this dot's going up and down. Can you see it? Yeah, yeah. If you can't see it from where you are, move over here. But it's also moving slowly across over time. Now what I can do is make it move faster, and when it does that, then we can see, if I do it fast enough, it can sort of capture what's going on with the sound wave. Oh, this is better. So you can see when I talk that I don't really make sinusoidal waves, but you can see the disturbance. Yeah? Okay. If we wanted to make a sinusoidal wave, how could I do it? Constant? What would have to be constant? Okay, so you're gonna go, ah! That was constant. Yeah, so what does it sound like if you repeat? I need to make a tone, right? So, I don't know if I can do this. Ah! Oh, that's awful. Okay, I can whistle. Oh. That was better. Okay, so that was almost a sine wave, right? Okay. If you want, I'll leave this on later, and you can play with it, and you can see what your voice looks like, and also what sort of tones you can make. Okay. What was that? Oh yeah, okay. You'd want to do it longer. Okay. What other things make tones like that?
What, out of your mouth or?
Oh, I don't know. Well, we got this device now that can measure things. We should make a few tones and see what they look like.
I think a chime.
What does it?
A chime.
A chime?
Do you have it?
See if you can make that aluminum rod or something.
Yeah, let's do that. Oh, yeah.
Pay attention, dude.
What was that?
Oh, look at that. Wow. It didn't work all that well, did it? I got a few other things. I have some tuning forks. Yeah. Oh, there we go. So it's not very good. Yeah, it didn't work as well. Okay. Other ideas? All right. Oh yeah.
So, one of my favorite Beyonce songs.
Oh, yeah, yeah. We get the same thing as like
And it was plastic.
up and
Have a glass one?
Yeah, we try to learn our steps.
You like stick your finger in the water and be like, glass around the
Yeah, without like losing the weight, yeah.
I did like
Why do you
I
sing
have
like
friends
this?
that are like,
Oh.
super.
I did that one of the
me out.
Oh yeah,
All right,
they'd love me then.
yeah.
Because at one point I was really
You can
practicing
find something
Halo,
you can do it.
Oh,
singing
yeah.
Halo, trying to just like, yeah, right. I could do it. I could literally hit all the notes.
They would love you.
It was pretty
So-
fire. I spit hot fire. I'm not gonna lie.
For our perception, okay, with sound, what difference does, well, changing the frequency? How do we perceive that? Yeah. It's high pitch, right? Okay, so, let's see, if I can. That's a particular frequency. Let me see if I can do a lower one. Yeah, not so good. One of the things I have over here is a function generator. What it will do is it's also got a paper cone speaker like this, and what it does is it sends an electrical signal to the coil, which creates a magnetic field. Remember, there's a permanent magnet in here, which causes the speaker or the paper cone to move one way or another. Okay? If it does it so many times per second, that makes a sound wave that many times a second. So I can adjust this. Okay? And right now it says that's 453 times a second. If I make it go faster, what do we think is going to happen? It's going to be louder? Higher pitch? Higher pitch, louder? Are they the same thing? No. What's different? Loud, yeah, okay. Loudness is amplitude, okay? And so, let's see. I've got this one here. I'm gonna change the frequency. Okay, so now it's getting higher, lower. Yeah? Higher, lower. All right? I'm going to change the amplitude. Okay? This is lower, higher, lower, higher. So the pitch that you hear doesn't change, but it gets quieter or louder. Yeah? I can. Oh man, that makes it. Okay. Oh, right. There we go. Oh, yeah. Okay. Because this is a nice regular repeating thing, I can trigger on it, and it repeats this sound. So we can go, well, what happens to the, if I change the frequency and make it higher or lower? Okay. You can see that what I'm doing is sort of compressing these together or stretching them out. Well, that's okay. If I change the amplitude, okay, I'm doing this, right? I'm changing I'm changing the amplitude, I'm changing the loudness, but the pitch is still the same. Right? Okay. So those will affect the sound. I can also go really high. Yeah. lower frequency, higher frequency. We can see how this works. Be back here. All right.
Did you have another organic box?
Okay, so if we talked about what determines the speed of waves, okay? And we said that
What are we doing? Free?
we said that for something like this spring, or a string, that the velocity is equal to the square root of the tension divided by the mass density. Okay. Sound waves have a speed. It's determined by the pressure of the air, okay, which is sort of like the force, okay, that is squishing the air together, the tension on this, okay, and it's also determined by the density of the air. Have you ever done things like gone to a helium tank and inhaled, and then, or a helium balloon, and then started talking?
Oh, yeah.
And if you do, your voice
I've
sounds
inhaled a lot more than that.
right? Squeaky and high pitched, even though you're talking in the normal way that you always do. Yeah? Okay? So that's because the pressure is still the same. Okay? It's still the same. You know, it's not high pressure helium or low pressure helium, but the density of the helium is lighter than the density of regular air. Okay? And so it ends up being a higher pitch. Okay? If you were to inhale some heavier thing, then your voice would be lower without trying, without, it just normally would go up or down depending upon that density. Okay? Your book doesn't talk about it, and it involves some more pressure and fluid dynamic stuff. Okay, but so typically, and also the speed of sound doesn't vary by much, okay, if you're in the air on the surface of the earth, okay, at standard atmospheric pressure, at regular room temperature, okay, the speed of sound is about 343 meters per second. Okay. So that's pretty fast, right? It's it's fast enough that I can talk, and you being, maybe 5-6 meters away from me, hear it pretty quickly. You don't think, oh my gosh, there's a long delay. Okay? But sometimes you do notice things where light also travels. Light travels really, really fast. Okay? Light travels at like 300,000 kilometers per second. Okay? It's very fast. Okay? So for things, or if sometimes you'll have the experience of you'll see something and then you'll hear it later. You have an airplane fly overhead. You see where the airplane is, and then you'll hear the sound as if it's following it. Okay, and that's because the airplane may be a few kilometers away from you. It may take at 343 meters per second. It takes about 3 seconds to go 1 kilometer. Okay, so if it's a few kilometers away from you, you might hear the sound as if it were following it by 10 or 20 seconds. Okay, so that's created by the dynamics of how the air pressure works. This is created by the dynamics of the tension and the mass of the spring. Okay? But there's another relationship involving velocity that really just comes from the geometry. Okay? If we are thinking about if we've got a traveling wave, okay, and we've got a lot of peaks, and so here's one wavelength, and here's the next wavelength, and they're all traveling along like that, okay? Well, if the wavelength is how lambda is the number of meters per cycle, okay? Okay? And the frequency is the number of cycles per second. Okay? So if the waves are traveling, okay, if during one period this peak travels over here, okay, and it's gone one period, okay, after the time it's gone through whatever the frequency number of periods, okay, then it will travel for 1 second, right? And so that will give you how many meters per second it is. So you can say that the velocity is equal to lambda f, okay? If this meters per cycle, cycles per second, this is meters per second, okay? And this is really just from the geometry, not the dynamics, okay? And so it would apply to any traveling wave situation, okay? So if you want to know if you say, you might say, all right, this this is 388 cycles per second, okay? So if it's 388 cycles per second, what's its wavelength? So F is 388 cycles per second, and V is equal to lambda F. Then I could say lambda is equal to F over V, which would be 388 over 343, which is going to be a little bit more than 1 meter, right? Okay? So that says that if we could visualize these sound waves, okay, I would have, you know, maybe one peak coming out, and then a meter away would be the next peak, and about a little bit more than 2 meters away would be the second peak. Okay, that's how they're spaced. Okay, if I
Did you finish? Nice. What calc are you in? Calc 3D.
And VDub is like 3 and 4 combined.
Oh, you're doing VDub calc?
Yeah. It's not that bad.
Yeah.
Yeah. Because like we use WebAssign. The problems. You didn't have to go to class. Yeah.
Oh,
Just
yeah.
I turn it down
I've got a
to
couple teachers like that.
281, okay, and the waves are spacing out. I turn it
My
up higher,
calculator
they get
teacher is
closer
like that.
together.
My calc 2.
Am I backwards?
Calc 1.
It's like upside down.
Calc 2. Dude, I like it.
No, but this shit is like easier.
Really?
Yeah. This is easier.
That's what everyone said. Like calc 2 is like apparently the hardest transition.
Yeah.
Like
Right.
calc 1 was fine for me, but calc 2 literally like I felt like I was busting my ass
Yeah.
and like getting a C.
Yeah.
And then it came down to the last test, and I knew I was gonna fail it. And something happened. And I was just
So it's
like,
going to be a little bit less than a meter.
Yeah, this is not that bad.
But,
You can just like,
thank you.
yeah. All you have
Yeah.
to do is just like, understand it and just repeat it over and over again.
yeah.
Like with intervals, like, just
Dude, integrals. There were so many applications of like an integral. And
Okay,
then
so the per seconds
I
canceled,
know.
and we end up with just meters.
integrating something was easy, but then like doing like every other part of math,
No,
I was
wavelength
trying to
is
do
just
like
meters.
figuring out like distances and like things
Okay,
like that.
it's
That's just
the
how it's
distance
so.
from one peak to the next peak,
Yeah.
from one
This
drop
shit
to the
is
next.
it's just like,
Okay.
yeah, you have to find
Cool.
distances, but like in a 3D graph.
Mm,
Yeah,
Cool.
it's not that bad.
cool. Okay.
Okay.
I remember we did it for years.
When a wave travels, shaking this, right? Okay? And then the shake basically propagates down the end of the line, okay? And so the wave can be a means of transferring energy, right? I expend some energy there, and if you were down over here and had something that could, maybe capture, this shaking from the crank or something, you could use it to send energy from here to there, right? And actually we use waves, or we take advantage of the fact that waves send energy. We get a lot of energy from the sun, either by growing plants or stuff like that, where the energy was produced over there, and it goes through a light wave and then comes over to us, right? Okay, so anyway, the radio signals, you can think of them as you're sensing, some energy that was produced at some transmitter, and you're sensing some of it further away, and that's what's delivering your data. So we can think about the waves as a means of transferring energy. If it's as the wave goes through, okay, the concentration of the energy might change, okay? So let's, with this, okay, if I pluck something over here, okay, and the disturbance goes down this spring, okay, all of it goes down the spring, okay? So if I shake this by a certain amount, I get the same intensity shake over there minus whatever little frictional loss happened along the way, right? Okay, but that might be pretty small, and in this case, it's not too bad. Okay, the biggest frictional loss is when it hits that pole on the other end and shakes. Okay, now if I come to this water tank, okay, and I disturb it, okay, and the ripples go. The ripple goes in a lot of different directions, right? So if I were to say I want to send some energy from where I plopped my finger in to a spot over here, well, a lot of the energy is going to all these other different places, right? So it's spreading out, okay? So what we would say is that the intensity is being reduced because the wave is spreading out. It's going off in 2 dimensions, okay? Sound waves have the same issue, okay? If I talk, and it's louder right next to me, okay? And the people that are closer think that I'm a little louder, and people that are further away are less, because the energy per square meter, okay, is dropping off. Over here, the energy just goes one way. Over here, the energy gets distributed basically in a circle. There's this expanding circle, and if I deliver, say, 1 joule of energy here, okay, it would spread out, okay, all the way around here, and I get, so many joules per meter. If I were repeatedly doing this, okay, in joules per second, power, maybe I'm expending so many watts of thumping the water, okay, I'd get so many watts per meter at a further distance away, okay? Does that sound reasonable? Alright. So, we can say, all right, there is some object and it's creating some sort of waves. It's waves with some power P, okay? And if it's just on a spring, okay, we would expect over here to get heat, right? Minus whatever little frictional losses we have, okay? If it's water waves, we'd say, all right, this is some source that's producing waves at power P. Those waves are spreading out in a circle. Okay? And if I look at some little chunk over here, okay, then the amount of power per watts per meter, okay, I get so many watts per meter, okay, and that would be P over, if we say, this is some distance R, some away, watts per meter would be the total number of watts that were produced over here, divided by this whole circle. Okay, so that would be divided by 2 pi r. Okay, so I'm going to do the next step. Suppose we've got some object that's producing waves of particular power, and this is producing three-dimensional waves like sound waves. Okay, the sound waves are going to leave this. These are supposed to be concentric spheres. Okay, and there you go. All right.
Cool.
So over here we had peaks, right? The peaks are spreading away. Over here, what we've got is the peaks form circles. So these are these ripples spreading out, okay? Over here, the peaks would actually be this shell, right? If I disturb the air and I make some sort of sound wave and it spreads in all directions, the peaks would move sort of radially away from me, not only this way, but that way, and that way, and that way. And it would form a sphere of where the peaks is, and it would get further and further away. Okay? If I go over here and I go, all right, I want to see how much power per square meter, so watts per meter squared, okay, I get over here, well that would be the power divided by the surface area, the original power got spread out over this whole surface area, and the surface area of the sphere is 4 pi r squared. Okay? So, let's see. This one, you just get the original power back, because it doesn't spread out. This one, you get whatever P over 2 pi r is. This one, P over the surface area. This has a name, which is called intensity. So we say the intensity of the sound wave is so many watts per square meter. Okay? I think this maybe ought to be called intensity, but it's not the same as that one. Okay, I'm not sure if this one has a name. Okay, but it is definitely the way that the power gets distributed. Okay, so the sound gets quieter, okay, it delivers less energy the further you get away. It's because of the three-dimensional nature that it's spreading out. And we could, you know, if we can measure the watts per square meter, we could quantify that intensity. It turns out that our ears are really very, very sensitive, and that we can hear, the quiet sounds that we hear are really a small number of watts per square meter, okay? Like a trillionth of a watt per square meter, okay? Which is not very much. And then we can also hear things, we can hear up to a watt per square meter, but that's kind of dangerous, okay? A thousandth of a watt per square meter is pretty loud, okay? But when you think about, the order, over 12 orders of magnitude, from a trillionth to something, louder, a thousandth of a watt per square meter, that's a big range. So, the first people to really quantify sound intensity, okay, were, well, when you think about sound intensity, does anybody ever work with it or know the name that we label for how loud a sound is?
Yeah.
Decibels, yeah, we use decibels, okay? So, decibel, that's one of the prefixes, right, for the metric system, right? Like you can have a decimeter, right, or a deciliter. It's not used all that often, but it means a tenth of, right? So this sort of implies that perhaps there's a unit called a bell. Yeah? And that this is a tenth of it. And it's true, it is. Okay? The original unit for you go, why don't people measure things with just watts per meter? The range is really high. So in order to compress the range, okay, and to try and get it to match up with how we feel about the way sounds are, very quiet sounds and very loud sounds, it's hard for us to imagine that's a trillion times louder than something else. But it's not so hard to say, well, this on a scale, this is between 100 or 50 or something like that. So in order to get the number smaller, what the Bell scale is you say, well, I'm going to say that a bell is equal to the intensity, okay? But we're going to use the log of the intensity. And we'll use the log of the intensity, we'll divide by some reference intensity. And because this was done around the turn of the century, okay, and before easy natural logarithm tables were available, but there were lots of base 10 logarithm tables available. You know why there were lots of base 10 logarithm tables available?
What was
Right. Well, basically 10 because of your fingers, of course, okay? But the reason they computed them was they didn't have computers, and you could make slide rules out of them and do calculations using logarithm tables to make multiplication easier, like adding, okay? So they had a lot of log base 10 tables, so it's the log base 10 of this, okay? So that's what a bell is, okay? After Alexander Graham Bell, it was developed by the Bell Telephone Company, right? And then, okay, so this reference is called the threshold of hearing. And it is 1 times 10 to the minus 12 watts per meter squared, okay? Which is teeny, right? Okay, it's a trillionth of a watt per meter squared. Your book has a table of decibel values and what they correspond to, and so, well, here it says it's the threshold of hearing. It doesn't say it corresponds to something, but it says that, well, let's see. If you said, I want the intensity of the sound I'm measuring matches this threshold of hearing, that would be a bell of 0, right? Okay. If it's 10 times more than that, it would be a bell of 1. Okay. A bell of 1 is, they say, the person breathing at 3 meters. Okay? So imagine I'm standing away from you by like 3 meters, and you're listening to my breathing. Okay? Not labored, difficult breathing, but just normal breathing. my guess is that right now you can't hear it because there's too much other background noise. But imagine a really quiet room and that sort of thing. That's 1 bell or 10 decibels, okay? And then they say a whisper is 20 decibels, right? And it keeps going. By the time you get to a vacuum cleaner, it's 80 decibels. A jackhammer is 100 decibels, okay? Anyway, they get louder and louder and louder.
Is that beta or is that just a mistake on the frequency?
No, oh,
Bell is beta.
well, hang on. So that's a bell. What's a decibel? Okay? The decibel is the beta, okay, on the equation sheet. And what we'll say is that beta is, well, for every bell, it's 10 decibels. So it's 10 times the log base 10 of the intensity over the reference intensity. Okay? So if you have something that is 70 decibels, okay, it's 7 bells, okay? So I divided by I naught would be 10 to the 7th, okay? Good. All right. So anyway, it turns out that by labeling these sounds like that, you can by labeling sounds with decibels, you can get an idea of how loud something is without using numbers like trillions and stuff like that. So I have this, which is it's the Radio Shack sound level meter. Okay, it measures things in decibels. Now, in order to use it, what I do is I tell it. Well, right now, I tell it a certain range that I think it might be, or at least I turn it to where I see the meter going. So right now, the meter is bouncing back. Sometimes the 0 is in the middle, and I've got -10 over here and +6. So if I keep it right at the middle, then it's at whatever this range value is, which it says is 80. Okay. Now that's probably me talking right at it. If you guys, start talking. Do I start talking?
No, I don't really want to start talking.
Now you're not as loud as me talking directly into your ear. So if I'll turn it down to 70, and now you guys talk.
What's up? How you doing?
You did not get it to 0. You didn't get it to 70. You're in the
How many
60s.
studies?
Yeah.
Screwing it up.
Okay.
No,
I've got it down in the 60s. I'm reading the meter, but when I
because the bulb's
stop.
already lit, fam.
You had the best
So your conversation is somewhere in the 60s. Yeah? Okay. So anyway,
I'm gonna piss down my basement.
if you're curious as to
So good.
what the sound is, decibel reading, you can, if it's something you can do in here, you're welcome to borrow this and check it out.
Yeah, you pass it around.
You should pass it around.
Sure. Check it out. Yeah, it's a nice toy.
Yeah.
We've been going for 56 minutes. We've been going for 56 minutes. Since
I didn't know what crown was actually in. A little piece of a crown. It's on your last one.
Take it with you. Well, don't forget my.
You need a sash.
Huh?
You need a sash.
No, that's, I like to keep it profile.
Yeah, keep it.
Otherwise, I could wear it around.
Oh, okay.
How are they supposed to know that? They'll just look inside. Oh, yeah, okay. Yeah, sorry. Royalty. Really, one of my good friends is royalty. She's related to the first king of Scotland. Yeah, it's crazy. There's probably still a little bit of incest in there, you know, a little bit of those genes, but
Okay.
he's great, man.
So, the last thing I have for class today is an appropriately themed, okay, in-class problem. Okay, so same rules as last time, okay, I'm happy, I would encourage you to work together, but I want everybody to hand in their own, copy of, their own version of the work, okay? All right.
What? Okay.
Nobody's coming to class on Monday, right? It's 4th of July. Okay,
Dude,
let's imagine that you go
I'm still
and you
coming.
watch fireworks. Okay, so you're watching fireworks.
If I was from my head doing homework,
What's that?
I'm doing homework.
Oh, yeah. Okay, so fireworks, no, these are like, they're going to be further away and louder. I hope, I mean, okay. Okay. Now,
Fireworks.
suppose you see a flash, and then six seconds later, you hear a
You're
bang.
When you're running, or just like in general?
That is,
I watched a video of this guy behind Kim Kardashian, he just like shows up. Just like constant.
75 decibels.
She does it for a good while too. Like for a good while.
And
Let me see.
how far away was the explosion?
We all have to turn in.
Well, it's 343 times 6. 1800. 2056 meters. Times that by 3.1. So what number is 2056 times 3.1. Alright, so what's 0.1 of 2056? 205.6. So 205.6. 2056 times 3. It's 6,160. Dude, add that together, 6,360, oh, 73.6. That's how far it away is, bitches.
What is that in?
What?
What's the unit?
Feet. This is feet. So then you divide this by 5,280, which is how many feet are in a mile, and you get 1 whatever miles. But
We don't understand the metric system, right?
yeah, so 2056 is how many meters is away. Hey, I just want to know for miles, okay?
How did you get miles in it?
So this is how much feet it's in. So if it's 353 feet per second of sound.
How did you end up with feet and miles?
Oh, this is meters. Well, I just converted meters to feet.
Why?
I don't know, to see how many miles it just did it.
Yeah.
It did it.
That's
Hey, you
not
did all that in
really
your head?
Yeah, what up?
You divided in your head too?
Oh, no, I didn't divide it. I didn't know this part. I don't know how to do this part. I don't know, this is like 1.1 or something. I don't know. But if it's 353, times that by 6, you get 2056, I think. I'm definitely not right.
My dad has like 20 horse.
Where's the explosion? We already know that one. What was the power of the explosion? I don't know. Oh, it was 2058. I was fucking. It's off by 2. I wrote 2056, and I can't do fucking math.
Damn.
3 times 6, 18. I just didn't have it.
You're close though.
Yeah, it was close. It was close.
There we go. All right. So
These horses text are going to be.
you're watching fireworks, you see a flash. 6 seconds later, it takes actually quite a while, okay, for a fireworks display, you hear a bang that's 75 decibels. Okay? All right? Now, how far away was the explosion? How far are you from the fireworks? What is the power of the explosion? How many watts, okay, was dissipated at the time when the fireworks blew up? How much energy is released, okay, if the explosion took place in 0.3 milliseconds? So in other words, this is a burning chemical reaction. Very quickly it goes bang, okay? So it did that in 0.3 milliseconds. How much sound energy was released, okay? And then part D says if the explosive charge that created that firework was equivalent to 3 Nobel sticks of dynamite, okay? A Nobel stick, Alfred Nobel, the guy who took the Nobel Prize, made all his money by making dynamite. Okay?
Nice.
And so he, do you know the story about Nobel? Okay.
No.
He, so essentially, Nobel saw people mining, okay? And he saw them using nitroglycerin to mine, which is an explosive compound, but it's unstable and it's dangerous, right? Okay? And so it can blow up without warning. So he decided, I want to find a chemical that's explosive, like nitroglycerin, but can be set off whenever you want it to and not accidentally. Okay? So he settled in on trinitrotoluene, which is CNT, which could be made into sticks of dynamite, which could be lit with a fuse, and did not blow up if you shipped them by train or dropped them or any other thing. Okay? So he thought, wow, this is cool. I've made the world a lot safer place. Mining is going to be better now that I've invented dynamite. Okay? And then people started using it in wars, making bombs. He felt horribly guilty. So to get over his guilt, he started the Nobel Prize. Okay. Do you know why there's no Nobel Prize for math?
Why?
His wife had an affair with math. He wasn't going to do that.
Is that really?
Guys,
Damn. I walked right into that.
so anyway, so a Nobel stick of dynamite has an explosive charge of 5 megajoules, or 5 million joules. Okay? So if this was a 3-stick, okay, explosion, okay, how efficient was it of converting that energy into sound? Good?
What is the power of this? Power.
The power.
Justice. And three-dimensional watts per meter squared is power is equal to 4 pi r squared. We know the distance, so we just have to algebraically rework p over 4 pi r squared equaling I to find out how much power is actually released.
Yeah.
X is equal to a column
I'm still back here.
Right? Is that?
Hey, sorry, this is what I get for trying to do this off the top of my head. I should use, you know, the reason I make formula sheets is because I can't remember the formulas, okay? And, yeah, I should look them up.
What? I? So we don't.